just looked up and wondered what's really going on up there? I mean, the sky is full of these incredible, sometimes really baffling sights. But what if I told you that with just a couple of scientific clues, we can solve some of its biggest mysteries? So, yeah, let's play detective for a few minutes and get to the bottom of it all.
Okay, first up, the absolute classic. We see it every single clear night, right? Those distant stars seem to flicker and dance in the sky. So why do they do that? And here's where it gets weird. In that exact same sky, you've got planets like Venus or Mars, and they don't twinkle at all. They just shine with this calm, steady light. What's up with that? What makes them so different?
And hey, these puzzles aren't just a nighttime thing. Get this, when you see the sun pop up over the horizon in the morning, it isn't actually there yet. Seriously, it's like a daily magic trick our planet plays on us. How is that even possible?
And of course, the big one. The question every single kid has asked, and honestly, most of us adults have probably struggled to answer. Why is the sky blue? It seems so simple, but the answer is fascinating. All right, we've got our questions. Let's start digging for clues. So, our first major clue is all about the air around us. I want you to try and think of our entire atmosphere as one giant, invisible, and kind of wobbly lens that all light from space has to travel through just to get to our eyes. Now, the fancy scientific name for this is atmospheric refraction, and all it really means is that light bends. It bends when it passes from one thing to another. And our atmosphere, it's not one solid thing. It's this messy mix of hot and cold air, thick and thin layers, and it's all constantly churning and shifting around. And check this out. As the light from a star hits our atmosphere, all those layers of air bend it, usually downwards. So our brains, which expect light to travel in a straight line, trace it back, and we see the star in a place it's not. It looks like it's a little higher in the sky than it actually is. It's basically a giant optical illusion we see every single night. And here is the absolute key to everything. That bending of light isn't a nice, smooth, constant thing. Why? Because, as it says here, the atmosphere is not stationary. It's always moving, it's turbulent. You've got pockets of hot air and cool air swirling around, making that light path jiggle.
And boom, this solves our first mystery. See, stars are so mind-bogglingly far away that to us, they're just a single point of light. As that tiny pinprick of light zips through our wobbly, turbulent atmosphere, its path gets jostled around constantly. And to our eyes, that constant wavering looks like a flicker, a twinkle. But planets? They're way, way closer. They actually look like little disks, not points. So even though the light from each part of the disk is wobbling, it all averages out, The effects cancel each other out, and what we see is a steady, solid glow. Case closed on that one.
Okay, so now let's take that same exact idea, atmospheric refraction, and use it to solve our sunrise mystery. Just look at how this works. It's the same principle. When the sun is still physically below the horizon, our atmosphere grabs its light and bends it right over the curve of the Earth to where we are. So we are literally seeing an image of the sun before the actual sun has cleared the horizon. It's wild. And we're not talking about a few seconds here. This effect means we see the sunrise a full 2 minutes before it actually happens. And on the other end of the day, it means we can still see the sun for about 2 minutes after it is set. So our atmosphere gives us about 4 extra minutes of sunlight every single day. How cool is that? All right, 2 mysteries down, 1 to go. And to solve the big one, the case of the blue sky, we need a brand new clue. This one isn't about bending light. It's all about scattering it. So what in the world is scattering? Well, just imagine sunlight barreling into our atmosphere and slamming into all the tiny, tiny particles floating around in there. We're talking about things as small as the molecules of air themselves. These little particles basically catch the light for a split second, and then they spit it back out, but in a totally random new direction. They scatter it all over the place. Okay, but how does this actually work? Well, here's the crucial detail. It turns out that not all colors of light get scattered equally. The tiny molecules of nitrogen and oxygen that make up almost all of our air are the absolute perfect size for grabbing and scattering light that has a short wavelength. And this pretty much says it all. Remember, sunlight isn't just one color, it's all the colors of the rainbow mushed together. You've got red light with its long, lazy wavelengths, and you've got blue and violet light with their short,
energetic wavelengths. And as you can see, those little air molecules are way better at scattering that short wavelength blue light than they are at scattering the long wavelength red light. It's not even close. So, we've got our clues. We know our atmosphere bends light, and we know it's a champion at scattering blue light. Let's put these two ideas together and finally crack the case of the blue sky. So here's how it all goes down. First, sunlight, with its full mix of colors, enters Earth's atmosphere. Instantly, the tiny air molecules start scattering that light. But, and here's the key, they are way, way more effective at scattering the blue light. So they throw that blue light in every possible direction. Up, down, sideways, you name it. Which means that when you look up at any part of the sky, you're seeing all of this scattered blue light coming at you from everywhere. The sky itself is basically glowing blue. And this right here just drives the whole point home. If you took away our atmosphere, there'd be nothing to scatter the light. And that's exactly why pictures from the moon or from astronauts in orbit show a completely pitch black sky even with the sun shining right there. No atmosphere means no scattering, which means no blue sky, just darkness. So there you have it, mysteries solved. But wait, that brings up one last really cool question. If all the blue light is getting bounced all over the sky, what happens to the red, orange, and yellow light that doesn't get scattered as well? I mean, where does all that leftover color go? Well, here's a hint. If you've ever watched a beautiful sunset, you've already seen the answer.